All right, in this video, we're going to talk about suggested homework problems in 8.6, where we talk about numerical integration techniques for definite integrals. You've already talked about some approximation techniques in chapter 4 with lower sum and upper sum and the midpoint rule. And that was the midpoint rule was somewhere between the upper sum and the lower sum and was your best estimate that you could get so far. These are going to give you better estimates without going as far as doing the limit definition of the antiderivative and getting infinitely many rectangles. But like that definition, if you took infinitely many of these intervals for the trapezoidal rule or for Simpson's rule, you would also get the exact answer. So starting with number 1 here, let's just talk about if a numerical integration technique is appropriate for this integral here, or is necessary, let's say. And the answer is no, it's not necessary, because this is something where our basic differentiation rules apply and we can get an exact answer. We only need to use numerical approximation techniques when the integrand is not able to be integrated with any of our basic differentiation rules that we have. We'll learn some other techniques moving forward that may help us when we don't recognize any of the basic rules. In the next section, we'll talk about integration by tables. I don't want to get ahead of myself, but that will be really helpful, that we have something like 100 rules in the back of the book that we can look at and try and match a form for. And most of the time that's going to be sufficient for us. There's even bigger tables that have something like 150 rules in them. If you don't find what you want in the table in the back of your book that has 100 rules to it, then you can look online for integration tables. And I'm going to show you that in some of the problems today that you can just go ahead and you can use a calculator, even like your TI-84, and it'll give you a numerical approximation for your definite integral. So that'll be one of the problems that we do later. Let's start with number 3 now. And all of these are going to be things that we could find the exact value of, but we're going to approximate them first with our 2 techniques. Oh, I didn't show you the 2 techniques. Trapezoidal rule, I'll abbreviate TR, is going to be that the definite integral from a to b of f of x dx is equal to 1/2 of delta x times f of x0 plus 2f of x1 plus 2f of x2 plus ... plus 2f of xn minus 1 plus f of xn. And I know I kind of cramped that in there, but there's ones on the outside for our x0 is equal to a, and our xn is equal to b, and everything in the middle here is going to have a multiplier of 2. Our delta x, which is our distance between these x values, is equal to b minus a over n, and we're going to multiply on the outside by half of that delta x. And this is related to the area of a trapezoid. Don't worry too much about it, about how it was, how it came about. That's explained in your book if you're really interested in that. Simpson's rule, which I'll abbreviate SR here, is going to be a to b of f of x dx, and it's 1/3 delta x times f of x0 plus 4f of x1 plus 2f of x2, and this pattern of 4, 2, 4, so on continues, plus ... plus 2f of xn minus 2 plus 4f of xn minus 1 plus f of xn, and we're done. And in Simpson's rule, n must be even to use Simpson's rule. Now I'm going to use my calculator for pretty much everything in this, and you should too. We should not be trying to find things on a basic calculator and rounding decimals and then using the rounded decimals to get another rounded answer and getting rounding error on top of rounding error. I'm just going to let the calculator do pretty much everything for me. So one of the features that's in your calculator, I'm going to show you the old way to get to it first. If I put the function and y equals here, and I want to evaluate it at a specific value, the old way is to go to vars, y vars, function, call up the function name, and you can stick in a value into it like so, and you can get a decimal approximation, but the calculator knows the exact value that's there. And the newer calculators that have some special features that are not even listed here, that they have this F1, F2, F3, F4, so on, that are in the green here with the alpha. If you hit alpha Y4, there's all of your function, your Y var things, and it will show depending on what mode you're in, so you don't have to select the mode. And I can just grab the function name out of there because I'm going to be using it over and over again. So I'll be using that shortcut on my calculator since I have a TI-84 Plus CE application here. And if you don't have a TI-84 Plus CE, that's okay, as long as you have a TI-83, TI-84, or TI-84 Plus. Maybe your TI-84 Plus will let you go into alpha F4. If not, just go into the vars menu, arrow over to y vars, and find the function name. So I'm going to write things out the way that I'm going to enter them into the calculator. All right, number 3. So we're approximating 0 to 2, x2 dx, n equals 4. So delta x is equal to 2 minus 0 over 4, which is 1/2, and I'm going to estimate that as 0.5. So then I'm going to say that trapezoidal rule here is going to be half of 0.5 is 0.25 times, and so I'll put another set of parentheses here, and then that's going to be y1 of 0 plus 2 times y1 of 0.5 plus 2 y1 of 1 plus 2 y1 of 1.5 plus y1 of 2. I'm going to type it in like that. So let's let my calculator tell me what this is. 0.25 times alpha F4 Y1 of 0 plus 2 alpha F4 Y1 of 0.5 plus 2 alpha F4 Y1 of 1. Oops, I need to put parentheses around that, of 1. This is function notation. Plus 2 alpha F Y1 of 1.5 plus alpha F4 Y1 of 2, close parentheses for the multiplication that's out front. And go to, where did I miss a parenthesis? Oh, this is x squared. I forgot to put the function in there first. All right, let's come back up here. There we go. So this is 2.75. Don't forget to put your function in y equals first before you do this. So now I want a third of a half as a sixth. So I'm going to come here and I'm going to make this, say, 1 divided by 6. And then I'm going to change this 2 to a 4. I'm going to change that 2 to a 4. And I'm done. And that will be Simpson's rule is going to be 1/6 times y1 of 0 plus 4 y1 of 0.5 plus 2 y1 1 of 1 plus 4y1 of 1.5 plus y1 of 2. And this is approximately 2.6667 when we round to 4 decimal places. The assignment here wants us to round everything to 4 decimal places, even if it terminates before the 4th decimal place. The exact value here is going to be integral 0 to 2 x squared dx is 1/3 x cubed. Evaluated from 0 to 2 is 1/3 of 8 minus 0 is 8/3, which is approximately 2.6667. Show you that 8/3. There we go. So Simpson's rule is the best approximation. Let's go ahead and let's look at number 5. Let's put our function in here. This is the one that I had in there just a second ago. 1 over x minus 2. So delta x is 4 minus 3 over 4 is 1/4. So now I need, I'll just leave things as fractions. If I need to, but since it has an exact decimal, then I'll come here and say trapezoidal rule is going to be half of this times y1 at 3 plus 2y1 at 3.25 plus 2y1 at 3.5 plus 2 times y1 at 3.75 plus y1 at 4. We'll close that up there. So 0.125 times, and then y1 of 3 plus 2 times y1 of 3.25 plus 2 times y1 of 3.5 plus 2 times y1 of 3.75 plus y1 of 4 to let's see. Oh, right here. So this is approximately 0.6970. And then with Simpson's rule, we come back and make an adjustment for the multiplier, that it's 1/3 of a 4th is a 12th. So 1 divided by 12. And then we make this to a 4 and make that to a 4. And we have Simpson's rule is equal to 1/12 of y1 of 3 plus 4y1 of 3.25 plus 2y1 of 3.5 plus 4y1 of 3.75 plus y1 of 4. And that's approximately 0.6933. And then we find our exact value. ln of the absolute value of x minus 2 evaluated from 3 to 4 is exactly equal to ln of 2 minus ln of 1. ln of 1 is 0. ln of 2 is approximately 0.6931. And you see that Simpson's rule is the closest to the exact value. Let's look at number 7. One to 3 of x cubed dx, n equals 6. So don't forget to come up here, change your function to x cubed, enter, come on out here, clear this. We have delta x is equal to 3 minus 1 over 6 is 2 over 6 is 1/3. So I might need to use fractions here. Let's use a number line to help me go 1, and then 3/3 plus 1 is 4/3, plus 1 is 5/3, 6/3 is 2, 7/3, 8/3, and then 9/3 is 3. So those are my x values that I'm going to need. Notice that I take 1, 2, 3, 4, 5, 6 steps because n is equal to 6. So trapezoidal rule here is half of a third is a sixth. And then this is going to be y1 of 1 plus 2y1 of 4/3 plus 2y1 of 5/3 plus 2y1 of 2 plus 2y1 of 7/3 plus 2y1 of 8/3 plus y1 of 3. So we have 1 over 6 times y1 of 1 plus 2y1 of 4/3 plus 2y1 of 5/3 plus 2y1 of 2 plus 2y1 of 7/3 plus 2y1 of 8/3 plus y1 of 3, and I get 20.2222 for Simpson's rule. This is going to be a 12th of y1 of 1 plus 4y1 of 4/3 plus 2y1 of 5/3 plus 4y1 of 2 plus 2y1 of 7/3 plus 4y1 of 8/3 plus y1 of 3. So let's come back here and make those edits. If you can't go over the row and highlight it like I just did, you can hit second entry and it should pull it back up for you in your calculator. So make that a 1/12. Make this 2 a 4. Keep that a 2. Make that a 4. Keep that a 2. Make that a 4. And then keep that a 1. And this should be Why did I say 12? Did that before. It's 9. It's a third of a third is a ninth. It's 20. This should be a ninth. 20.0000. And then the exact value of 1 to 3 of x to the third dx is 1/4 x to the fourth. From 1 to 3, so 1/4 of 81 minus 1 is exactly 80 over 4 is 20, which we'll call 20.0000 for this assignment because we're supposed to go to 4 decimal places on everything. Look at number 9. Nine says 4 to 9 of the square root of x dx. Let's make y equal to the square root of x. Clear all this. We have n is equal to 8. Make my number line here starting at 4. We have 9 minus 4 over 8 is 5/8. So I'm going to call this 32 over 8. When I add 5 to it, it's 37 over 8. I add 5 to it, it's 42 over 8. I'm not even going to try to reduce my fractions here because I am going to let the calculator do everything. So 67 over 8, and then 72 over 8 is 9, where I want to stop. So I'll just leave this all this way. I'll even call that 32 over 8 to be consistent there. So this is going to be 1/2 of delta x that I need is going to be 5 over 16. And 1/3 of delta x that I'll need later is going to be 5 over 24. So for trapezoidal rule, I'll have 5 over 16 times y1 of 32 over 8 plus 2y1 of 37 over 8 plus 2y1 of 42 over 8 plus 2y1 of 47 over 8 plus 2y1 of 52 over 8 plus 2y1 of 57 over 8 plus 2y1 62 over 8 plus 2y1 of 67 over 8 plus y1 of 72 over 8. This is 5 over 16 times y1 of 32 over 8 plus y1 of 37 over 8 plus y1 of 42 over 8 plus y1 of 47 over 8 plus y1 of 52 over 8 plus y1 of 57 over 8 plus, oh, this is, I forgot my 2's, 2, 2, 2, 2, 2, 2, y1 62 over 8 plus 2 y1 67 over 8 plus regular y1 72 over 8, close that, and I get approximately 12.6640. So Simpson's rule is going to be 5 over 24 times y1 32 over 8 plus 4y1 37 over 8 plus 2y1 42 over 8 plus 4y1 47 over 8 plus 2y1 52 over 8 plus 4y1 57 over 8 plus 2y1 62 over 8 plus 4y1 67 over 8 plus y1 of 72 over 8. Let's make our edits here. 5 over 24. Then let's get rid of that. I thought I got all the way to the beginning and didn't. 5 over 24. Then this is 4, 2, 4, 2, 4, 2, 4, 1. It's going to be 12.6667. Let's get an exact answer for number 9. 4 to 9 root x dx is x to the 3 halves, 2 thirds. 4 to 9 is 2 thirds of 3 cubed minus 2 cubed is equal to 2 thirds of 27 minus 8. 19 times 2 is 38 over 3. 38 over 3 is about 12.6667. All right, let's look now at number 11. So 11 says 0 to 1 2 over x plus 2 quantity squared dx, n equals 4, clear, y equals, clear, 2 divided by x plus 2 quantity squared, and delta x is equal to 1 minus 0 over 4. It's 1/4. So we have 0, 1/4, 1/2, 3/4, and 1 is our x values. Let's go ahead and look at 1/2 delta x is an eighth, and 1/3 delta x is a 12th. Trapezoidal rule says 1/8 of y1 of 0 plus 2 y1 of a quarter plus 2 y1 of a half plus 2 y1 of 3/4 plus y1 of 1. So we have 1/8 of y1 of 0 plus 2 y1 of a quarter plus 2 y1 of a half plus 2 times y1 of 3/4 plus 2 times y1 of 1. It's going to be approximately 0.3629. Let's see, did I do all that right? Zero, quarter, a half, 3/4. That's not a 2. That's what's wrong. 3352. There we go. And then this changes from an 1/8 to a 12th. And then this changes from a 2 to a 4. And Simpson's rule, which is 12th times y1 at 0 plus 4y1 at a quarter plus 2y1 at a half plus 4y1 at 3/4 plus y1 at 1 is approximately 0.3334. Our actual value is 0 to 1 of 2 over x plus 2 squared dx is 2 integral 0 to 1 x plus 2 to the negative second dx is a negative 2x plus 2 to the negative first, evaluated from 0 to 1, negative 2 times 3 to the negative first minus 2 to the negative first is negative 2 times 1/3 minus 1/2 is 2 times 1/2 minus 1/3, which is equal to 2 times 3 minus 2 over 6, and 2 goes into 2 one time and into 6 3 times, so that makes that 1/3, which is approximately 0.3333. Let's look at 13. 13 is y equals x e to the negative x, clear this, and I have 0 to 2, x e to the negative x dx, n equals to 4. So we have 2 minus 0 over 4 is a half. We have 0, a half, 1, 3 halves, and 2 is our x values that we're interested in. Our 1/2 of our delta x is a quarter, and our 1/3 of a delta x, and we need that, is a sixth. So 1/4 of alpha y1 of 0 plus 2 alpha f4 y1 of 1/2 plus 2 alpha y1 1 plus 2 alpha y4. This is 3 halves plus y1 of 2 is trapezoidal rule is going to give me 0.5706. And then I'll modify Simpson's rule here to give me 1/6 of, and this is a 4, it's a 2, it's a 4. Leave that one alone. So Simpson's rule says 0.5930, and the exact value, I'm leaving myself some space here. 0 to 2, x e to the negative x dx will require integration by parts. U equal to x, dv equal to e to the negative x dx, du is dx, v is a negative e to the negative x. So u, v is a negative x e to the negative x, evaluated from 0 to 2, minus the integral of v, which is a negative e to the negative x dx from 0 to 2. So this is a negative 2 e to the negative 2, minus a negative is plus, that's going to be 0. Then we'll have minus e to the negative x when we integrate, and this will be evaluated from 0 to 2. It's negative 2 e to the negative 2 minus e to the negative 2 plus e to the 0 is 1. So that'll be 1 minus 3e to the negative 2. 1 minus 3e to the negative 2 is approximately 0.5940. That's probably been the greatest error so far between Simpson's rule and the actual value. Let's look at 15. We have 0 to 2, root 1 plus x cubed. So the difference in this problem here, why it's in a different section, is we cannot solve this one with basic integration techniques. So we'll have to use the calculator to get the quote exact value that we're going to compare, but everything else is the same here. Delta x is 2 minus 0 over n is 4, is 1/2. So we have values of 0, 1/2, 1, 3 halves, and 4, which are going to be exactly the same thing as what we have up here. We just change our y1 to be cube root, square root of 1 plus x to the third. And I don't even need to bother to type all that again because that should be the same function there since I have the same number of intervals and same starting points. So it's 3.2832. And then this one should be Simpson's rule. Should be 3.2396. And then we're going to go into math. We'll see functional integration here. We're going to go 0 to 2. And then we've got y1. I don't want to type that all in again. Dx. And the exact value from the calculator is 3.2413. Let's look at 27. 27 says 2 to 4, 1 over x minus 1 squared dx, and we want to find for n equals 4, we want to find these approximations. So let's clear that. We have delta x is equal to 4 minus 2 over 4 is 2 over 4 is 1/2. So my values are going to be 2, 5/2, 3, 7/2, and 4. So my trapezoidal rule will be half of delta x is a quarter, third of delta x is a sixth. So we have a quarter of y1 of 2 plus 2 y1 of 2.5 plus 2 y1 of 3 plus 2 y1 of 3.5 plus y1 of 4. 0.25 times y1 of 2 plus 2 y1 of 2.5 plus 2 y1 of 3 plus 2 y1 of 3.5 plus y1 of 4 go to let's look at that again. 1/4 y1 of 2 plus 2 y1 of 2.5 plus 2 y1 of 3, 2 y1 of 3.5, y1 of 4. That looks right to me. 27. Oh, I'm finding the errors. Okay, I need to tell you the error formulas. We're not doing the regular rule here. So the error formula for trapezoidal rule error. My apologies are that the second derivative needs to be continuous. and defined, right? So, and we'll have the magnitude of the error is less than or equal to b minus a to the third over 12n squared times the maximum value of the absolute value of the second derivative. And for Simpson's rule error, fourth derivative must be continuous, and the magnitude of the error here is less than or equal to b minus a to the fifth over, I think it's 180, yes, 180 n to the fourth times the maximum of the absolute value of the fourth derivative of x here. So let's start by finding our derivatives. F of x is equal to 1 over x minus 2 squared for 27 is x minus 2 to the negative second. First derivative is negative 2 x minus 2 to the negative third. Second derivative is 6 x minus 2 to the negative fourth. Third derivative is negative 24 x minus 2 to the negative fifth. Fourth derivative is 120 x minus 2 to the negative sixth. So trapezoidal rule error here, I'll call it TRE, is going to be absolute value of E is less than or equal to B minus A. So A is 2, B is 4, N is 4. So that's going to be 2 cubed over 12 times 4 squared. And then let's graph these functions here. For the second derivative is 6 times x minus 2 raised to the negative fourth. And then for the fourth derivative is 120 x minus 2 raised to the negative sixth. Blue function is the first one that I'm interested in. Notice that on the, sorry, this is x minus 1, not x minus 2. 1, 1, 1, 1. 1 and 1. Try that again. There we go. So on the interval from 2 to 4, notice that it's decreasing here. And so that is going to tell me that my maximum value is going to be at 2. So trace 2. F double prime of 2 is 6. And then I'm going to trace, and I'm going to switch functions. And I'm going to evaluate at 2. This one is going to be 2 to the fifth over this is 180 times 4 to the fourth times, and then this is 120. Okay. So that is going to be equal to, let's come out here and see, 2 to the third times 6 divided by 12 times 4 to the second. No. 2 to the third times 6 divided by 12 times 4 to the second is, that looks like a quarter. And then 1/4, and then this is to the 5th. This is 120. No, this is, yeah, 120. And then this is 180. And that's to the 4th. That is math answer to fraction. That is a 12th. Both of those are the right answer. And that's it for this video. So we'll come back next time and we will talk about integration by tables. See you for the next video.